We know how to write the complex numbers in the Cartesian form, the x plus iy form. But now that we know how to get the modulus and the argument, we can write them in another form called polar form. Polar form is very useful because it's basically an index form. It's very useful in certain proofs and in certain solutions of problems. Let us suppose that the complex number z equals x plus iy has modulus r and argument theta, regardless as to the quadrant the point lies in. For simplicity, we'll take our point P to be in the first quadrant. So to plot that, we go across x and up y. Also the distance OP, that's the modulus, and the angle theta measured from the positive real axis and in the anticlockwise direction, that's the argument. So from trigonometry, we know that cos theta is x over r, so that x equals r cos theta. Sin theta equals y over r, so that y equals r sin theta. Hence, the complex number x plus iy can be written as r cos theta plus I times r sin theta. If we take the r out the front, we get x plus iy is r times cos theta plus I sin theta. This expression, cos theta plus I sin theta, is very important. For good reasons, which we won't go into here, we make the following important definition. We define e to the I theta to be equal to cos theta plus I sin theta. Hence, z equals r times cos theta plus I sin theta may now be written as z equals r e to the I theta. And when the complex number is written in this form, z equals r e to the I theta, where r is the modulus and theta is the argument, the number is said to be written in polar form. Let us consider the definition of e to the I theta again. It was e to the I theta equals cos theta plus I sin theta. And this definition holds for all values of theta. So we'll put theta equal to the value of pi. Then we have e to the I pi equals cos pi plus I sin pi. We know that cos pi is -1, sin pi is 0. So therefore e to the I pi equals -1 plus I times 0. Take the -1 across to the left-hand side. We have e to the I pi plus 1 equals 0. This result is e to the I pi plus 1 equals 0. Well, the formula contains a 0, which is vital for our number system, which is the Hindu-Arabic number system. It's because of the 0 we can write another numeral in a different place, and it means a different amount. So in one place a 3 will mean 30, and in another place a 3 will mean 3 million. We can do that because of the 0. The formula also contains the positive integer 1, which is the basis of all the other integers. So 2 is 1 plus 1, 3 is 2 plus 1, and so on. And from the integers, we get the rational numbers, which are in the form a over b, where a and b are integers and b is non-zero. So the fractions be built up from the integers as well. The formula contains two of the most important irrational numbers in all of mathematics. That's e and pi. They turn up everywhere. And it also contains the imaginary number I, which is the basis of the complex numbers. No wonder people regard this as one of the most remarkable formulas in all of mathematics. You've got to admit, it's pretty cool. Well, now that we know what the polar form is, and we know that it involves the argument and the modulus, let's do some examples where we'll change the Cartesian form into the polar form. And we'll do one example where we change the polar form back to the Cartesian form. Example 1 is to express 1 plus I in polar form. So we'll let z equal 1 plus I. Then r, the modulus of z, is given by r equals the square root of 1 squared plus 1 squared, which is the square root of 2. Remember that the modulus is the square root of the square of the real part plus the square of the imaginary part. Now, for the argument, we don't use a formula, we draw a diagram. We draw the diagram, and point P is in the first quadrant here. And from trigonometry, we know that tan theta is 1 over 1, which is 1. Hence, angle theta is pi on 4. And since the point P is in the first quadrant, the argument is positive and it's measured in the anti-clockwise sense. Hence, the argument of Z is also pi on 4. So, the complex number 1 plus I can now be written as the square root of 2 times e to the pi I on 4. Example 2 is express minus root 3 plus I in polar form. Again, we'll let Z equal minus root 3 plus I, and then R, the modulus of Z, is given by R is the square root of the real part squared, which will be minus root 3 all squared, plus the imaginary part squared, which is plus 1 squared. That comes out to the square root of 3 plus 1, which is square root of 4, which is 2. Again, for the argument, we draw a diagram. And from trigonometry, in the triangle, we see with alpha as the acute angle, tan alpha is 1 over root 3, and hence alpha is pi on 6. Therefore, the obtuse angle theta is 5 pi on 6. It's pi minus pi on 6. And since the point P is in the second quadrant, the argument is positive and measured in the anti-clockwise sense. So the argument of the complex number Z is 5 pi on 6. Hence, minus root 3 plus I can be written in the polar form as 2 e to the 5 pi I on 6. Example 3, express minus 1 minus root 3I in polar form. Well, again, we let Z equal a complex number, so Z is minus 1 minus root 3I. Then R, the modulus of Z, is given by R is the square root of minus 1 all squared plus minus root 3 all squared. And that's because the real part of Z is minus 1, the imaginary part is minus root 3. That comes out to the square root of 1 plus 3, which is the square root of 4, which is 2. Now, for the argument, we draw a diagram again, and from trigonometry, we see that tan of angle alpha, which is the acute angle in the triangle, tan alpha is root 3 on 1, which is root 3, hence alpha is pi on 3. That makes the obtuse angle theta equal to 2 pi on 3. And since the point P is in the third quadrant, its argument will be negative, and it's measured in the clockwise direction, the negative direction. The argument of Z, therefore, is minus 2 pi on 3. Hence, the complex number minus 1 minus root 3I can be expressed in polar form as 2 times e to the minus 2 pi on 3 times I. Example 4, express 2 root 2 minus 2 root 2I in polar form. Well, again, we let Z equal 2 root 2 minus 2 root 2I. So R, the modulus of Z, is now given by the square root of 2 root 2 all squared plus minus 2 root 2 all squared. That's the square root of 4 times 2 plus another 4 times 2, square root of 8 plus 8, which is the square root of 16, which is 4. For the argument, we draw a diagram, and we see that the point P, representing Z, lies in the fourth quadrant. And from trigonometry, we have tan theta is 2 root 2 over 2 root 2, which is 1. So angle theta is pi on 4. However, the point P is in the fourth quadrant, so the argument is negative because its argument is measured in the clockwise negative direction. So the argument of Z will be minus pi on 4. Hence, 2 root 2 minus 2 root 2I is 4 e to the minus pi I on 4. Example 5, we'll take a complex number in polar form and convert it back to Cartesian form. Our example will be to express Z equals 4 times e to the minus pi on 3I in Cartesian form. Now we know that e to the I theta can be written as cos theta plus I sine theta. So therefore we have that z, which is equal to 4 times e to the minus pi on 3 times I, that can be written as z equals 4 times all of cos minus pi on 3 plus I sine minus pi on 3. And now we know that the cosine function is an even function, so cos minus pi on 3 is the same as cos plus pi on 3. And the sine function is an odd function, so that sine minus pi on 3 is minus sine pi on 3. So we get that z equals 4 outside of all of cos pi on 3 minus I sine pi on 3. And then we put in the values for cos pi on 3 and sine pi on 3, and we'll end up with z equals 4 outside of all of a half minus I times root 3 on 2, and that comes down to z equals 2 minus 2 root 3 times I. It's time for me to have a break and for you to do exercise 1, which is to write the complex number z, which is minus 2 plus 2i, in polar form. So stop the video now and change it into polar form. I just give some guiding steps. Step 1, you will find the modulus of z. Step 2, you find the argument of z. And you do this by drawing a diagram and asking in which quadrant is the given point. What is the acute angle in the triangle? In which direction is the required angle measured, and find the required angle? Is the argument positive or negative? And then finally state the argument. And in step 3, you put everything together and state the polar form. The answer is 2 root 2 times e to the power of 3 pi I on 4. Did you get it right? Note, in Maple, you would write the answer as 2 asterisk sqrt with 2 in brackets, asterisk exp, and then in brackets you'd write 3 asterisk capital Pi asterisk capital I slash 4. Exercise 2 is an easy question. It asks you to convert a complex number in polar form back to Cartesian form. So stop the video now and write out that solution. It'll only take a few lines. What you should have written is that z equals root 2 outside of all of cos 3 pi on 4 plus I sine 3 pi on 4. And then that becomes the square root of 2 outside of all of minus cos pi on 4 plus I sine pi on 4. Put in the exact values for cos pi on 4 and sine pi on 4, and it all comes down to z equals minus 1 plus I. One of the advantages of writing the complex numbers in polar form is that it makes it a lot easier for us to raise it to a power. We'll give an example here where we take a complex number in Cartesian form, change it into polar form, raise it to the power, and then we can convert it back to Cartesian form. As an application of polar forms, we'll do example 6. This asks us to evaluate minus 1 minus I all to the power of 10. First of all, we'll let z equal minus 1 minus I. Therefore, the modulus of z will be the square root of minus 1 all squared plus another minus 1 all squared, which is the square root of 2. Now, to get the argument, we draw a diagram, and we'll let alpha be the acute angle between the real axis and the hypotenuse OP. By trigonometry, tan alpha is 1 over 1, which is 1, and hence alpha is pi on 4. So therefore the obtuse angle will be 3 pi on 4. But we know that the point P is in the third quadrant, so the argument has to be negative. Hence the argument of z is minus 3 pi on 4. Therefore, we can write z, which is minus 1 minus I, in Cartesian form. We can write it in polar form as square root of 2 times e to the minus 3 pi on 4 times I. Now we can write minus 1 minus I, all to the power of 10, as root 2 times e to the minus 3 pi I on 4, all raised to the power of 10. Now we know that when you have two terms multiplied together in a bracket and the whole bracket raised to a power, you raise the terms individually to the power. So we raise the root 2 individually to the power of 10 and the e to the minus 3 pi I on 4 individually to the power of 10 as well. And now we write the root 2 as 2 to the power of a half. And for the exponential term, we remember that when you have a term already in index form and it's raised to another power, you multiply the indices. So that becomes e to the minus 3 pi I on 4 multiplied by the 10. The 2 to the power of a half raised to the power of 10, once again we will multiply the indices to get 2 to the power of 5, and the power of e will cancel to get minus 15 pi I on 2. So at this stage we have 2 to the power of 5 times e to the minus 15 pi I on 2. We need to take this term, 2 to the power of 5 times e to the minus 15 pi on 2 times I, and write it in Cartesian form. Well, 2 to the power of 5 is 32, and 15 pi on 2 we'll write as 7 pi plus pi on 2. So we get 32 e to the power of minus all of 7 pi plus pi on 2 times I. Now we'll expand out the bracket in the index. So that will give us 32 e to the minus 7 pi I minus pi on 2 I. And now we'll use an index rule to break up the index in the term. So we'll get 32 e to the minus 7 pi I times e to the minus pi on 2i. That's using the rule that when you multiply terms in index form with the same base, you add the indices. We're actually using that one going backwards. Now we'll use another index rule that says when you've got a term in index form and it's raised to another power, you multiply the indices. So we will take that one going backwards as well and write 32 e to the pi I to the power of minus 7, because the power pi I times minus 7 is minus 7 pi I. So we use that index rule going backwards. And then we've got times e to the minus pi on 2 times I. But we know Euler's formula says e to the I pi plus 1 equals 0. And that was because e to the I pi is minus 1. So we can replace the e to the pi I by minus 1 and get 32 times minus 1 to the power of minus 7. And also we know that e to the I theta is cos theta plus I sine theta, so we can replace the e to the minus pi on 2i by cos minus pi on 2 plus I sine minus pi on 2. Now the minus 1 to the power of minus 7 is 1 over minus 1 to the positive 7, which is 1 over minus 1, which is minus 1. And also we know that the cosine function is an even function, so cos of minus pi on 2 is going to be cos of plus pi on 2. And the sine function is an odd function, so sine of minus pi on 2 is minus sine pi on 2. From this we get 32 times minus 1 times cos pi on 2 minus I times sine pi on 2. But cos pi on 2 is 0, sine pi on 2 is 1, so it all comes out to 32i. Are you ready to see if you've understood everything in this lecture? Well, let's look at exercise 3. It asks you to evaluate minus 1 plus I times root 3, all raised to the power of 11, and write your answer in Cartesian form. So stop the video now and attempt this exercise. I'll outline some steps for you for the solutions if you get stuck. Firstly, let z equal -1 plus I times root 3, and then find the modulus and argument of z so that you can write z in polar form, and you should have 2 times e to the power of 2 pi I over 3. Next, raise the polar form of z to the power of 11 and you will get 2048 times e to the power of 22 pi I over 3. Now, break up the improper fraction in the power of e. Well, for us that will be 22 over 3. You break it up into an integer plus a proper fraction. In this case, you'll break it up to 7 plus 1/3. And this gives that z to the power of 11 is 2048 times e to the power of 7 pi I plus pi I over 3. Next, break up the index in the exponential expression to give z to the power of 11 equals 2048 times e to the pi I, all raised to the power of 7, times e to the pi I on 3. Then use the results for e to the pi I and e to the pi I on 3 to obtain z to the power of 11 equals 2048 times -1, all raised to the power of 7, times cos pi on 3 plus I sin pi on 3. Finally, put in the exact values of cos pi on 3 and sin pi on 3 and simplify everything to get the final answer, z to the power of 11 equals -1024 minus 1024 times root 3 times I. Give yourself a pat on the back if that's the answer you got. I trust you enjoyed lecture 3 and that you're a lot clearer on the processes of converting complex numbers from Cartesian form to polar form and vice versa. If you haven't subscribed to the SlvenÄvslve channel, can you please do so? Now look out for lecture 4. It'll be in 2 parts, but what we'll do there is look at a lot of properties of complex numbers, and they'll give you proofs of them, both algebraically and geometrically. So look out for lecture 4. They'll be in 2 parts, part 1 and part 2. Also, at my website in SlvenÄvslve, we have practice quizzes and a final exam so you can do to see how well you've learned the material in the course.